Okay guys, in this video we are going to talk about multiple bonds in the valence bond picture, and those involve the overlap amongst multiple orbitals, not just two, but more than two orbitals between two atoms. So let's look first at an example. We'll look at ethylene. Ethylene has a double bond between the two carbons, so one of those is going to be a sigma type bond, and one of those will be a pi type bond. Now in this geometry, we say that the carbon atoms are sp2 hybridized, right? It's a trigonal planar structure according to Vesper, and it's the sp2 hybridization. So let's see where the two bonds between the two carbons comes from. So here is the atomic orbital diagram for unhybridized carbon. Right? You've got two electrons in the 2s orbital, and two electrons are in the 2p orbitals. One of the p orbitals is unoccupied. When we make the sp2 hybridization, we combine that 2s orbital and the two 2p orbitals to make three equivalent sp2 hybrids, and then there is one remaining unhybridized p orbital. Now we've got a total of four valence electrons, and so we're going to put each of those electrons in a unique orbital. So we have three electrons occupying the sp2 hybrids and one electron occupying the unhybridized p orbital. And then what we can do is we can pair two of these sp2 hybrids with a 1s orbital on each hydrogen. Okay, and so two of these sp2 hybrids make the single bonds that we see here between carbon and hydrogen, and then the remaining sp2 hybrid can form the single bond between the two carbon atoms. Right? That's what gives the molecule that trigonal planar structure. And then that remaining p orbital, that p orbital that's not participating in the trigonal plane, is actually coming out of the board at you. So you would imagine a p orbital that's going in and out of the plane of the screen. And each carbon atom has one of those. And those two unhybridized p orbitals can overlap with one another to form a pi type bond. Okay, and that's what's illustrated here in this diagram. So we have the three sp2 hybrids on this carbon atom and the three sp2 hybrids on this carbon atom. For each carbon atom, two of the sp2 hybrids overlap with the 1s orbitals on the hydrogen atoms, giving us two sigma bonds. The remaining sp2 hybrid orbital overlaps with the sp2 on the other carbon atom, giving us that single bond. And then what's being illustrated here, this is the p orbital that is perpendicular to the sp2 planar structure. And so we have good overlap above and below the plane of the molecule. And that forms a pi bond. We have overlap above and below. And that's the shape of a pi bond. And that's illustrated here in this sort of diagram. Here's another example, a different molecule, ethyne or acetylene. Acetylene has a triple bond between the two carbon atoms. Okay, and the triple bond is going to involve sp hybridization. So you're going to be combining, on each carbon, you're going to be combining its 2s orbital and one of the 2p orbitals. And that's going to give you, for each carbon, two equivalent sp orbitals. One that points in this direction, the other that points in the other direction. And then you are going to have unhybridized p orbitals that have electrons in them, right? Carbon has 4 valence electrons. So one electron occupies that sp orbital, another one occupies this one, and then each of the unhybridized p orbitals has a single electron that can participate in bonding. So what you'll have here for this carbon atom, one of those SPs is going to overlap with a hydrogen 1s orbital to form a sigma bond. The other sp orbital will overlap with an sp orbital of the neighboring carbon to form a sigma bond here. And then now we've got two unhybridized p orbitals on each carbon atom, and they overlap in a pi-type fashion, each of them. So we have one pi bond between this p orbital and this p orbital, and then another pi bond between that orbital and this one. Okay, so we get two pi bonds out of that. Right? The first one is a sigma, and then the other two are pi bonds. And notice how they are arranged relative to the structure of the molecule. The two pi bonds are perpendicular to one another. So we're being asked to consider an example. Here they want us to look at dinitrogen difluoride and describe the bonding that we see in the molecule. So I'm going to write out the Lewis structure. I think we're going to end up having a double bond here. Like so. And then we're going to have lone pairs on each nitrogen, and then we're going to have lone pairs, of course, on the fluorines. So each nitrogen here, notice that there's 1, 2, 3 electron pairs with respect to the Vesper structure. So each of these nitrogens is going to have a trigonal planar structure, which means they are occupying, they involve sp2 hybridization. Okay, so you can, I can draw the molecule in a different way. Let's go ahead and I'll put one fluorine coming off this way. I'm going to put the lone pair coming off that way. I'm going to put, we can imagine that we're sort of looking down on the molecule. We'll do the same thing. It doesn't really matter which way I put these at this point. And then there's going to be a pi bond here. So these p orbitals, these are coming out of the plane of the board, or out of the plane of the screen. So we have a planar structure involving the fluorine and the lone pairs. And then about each nitrogen, there's p orbitals that are coming up out of the plane of the page. And so they are overlapping to make the pi bond. So we have a sigma bond between the nitrogen and the fluorine that involves the sp2, that involves an sp2 hybrid on the nitrogen. Another sp2 hybrid on the nitrogen is being occupied with a lone pair. And then the third sp2 hybrid orbital forms a sigma bond with the other nitrogen. And we have the same thing on the other side of the molecule as well. In this example, it's a similar problem. We're being asked to describe the bonding in carbon dioxide. You may recall from our previous exercises that carbon dioxide is a linear molecule. Okay. It involves, we have two double bonds here. And so for the linear structure, we're going to have an sp hybridization. And so we're going to have, on carbon, we're going to have an sp hybrid. So the first bond here involves a sigma overlap between an sp orbital on carbon and an orbital on oxygen. Same thing on the other side. The first sigma bond would be the overlap of an sp hybrid orbital with an orbital of oxygen. And then this second bond here would involve the overlap of a unhybridized p orbital on carbon and a p orbital on oxygen. Likewise, you would have, for this bond here, we would have another unhybridized p orbital on carbon overlapping with the p orbital on oxygen. Okay, so that's the nature of the bonds here. We have two sigma bonds involving the sp hybrids, and then the second bond in each double bond would be a pi-type bond involving unhybridized p orbitals on carbon. In this example here, we're considering the structure of SO2. So they want to know what's the hybridization of sulfur on SO2. And so the Lewis structure that we get for SO2 would look something like this. You have a lone pair there. And then we could draw resonance structures for this as well. But I'm just going to stick with one structure here. So we have, essentially, we've got 3 Vesper electron pairs. And so this would be a trigonal planar structure. And then it would have sp2 hybridization. So this sigma bond involves an sp2 hybrid on the sulfur. The lone pair occupies an sp2 hybrid on sulfur. The first bond here within this double bond involves the sp2 hybrid, the third sp2 hybrid on sulfur, and then that remaining bond here in the double bond, that would involve an unhybridized p orbital on sulfur and then a p orbital on the oxygen. In this last example, we have a species that has an odd number of electrons. So NO2, nitrogen only has 5 electrons. Each of the oxygens contributes 6 electrons. So we are going to have a total of 17 electrons. So an odd number of electrons. We're not going to get an octet rule satisfied out of this. And the Lewis structure that you would come up with for it, there's several that you could draw, but here's one that gives as close to an octet as you can get on the nitrogen. This structure, I'm sure you can draw Lewis. You can draw several resonance structures. What would be the hybridization about the nitrogen atom for this particular Lewis structure? Well, again, you just treat this single electron as if it were an electron pair, according to Vesper. And so you have 1, 2, 3 pairs. Okay, so again, it's going to be trigonal planar. And so we would say it's an sp2 hybridization. Again, this sigma bond would involve an sp2 on nitrogen and an atomic orbital on oxygen. This single electron would occupy an sp2 orbital on nitrogen. This first bond of the double bond would involve an sp2 on the nitrogen and an orbital on the oxygen, and then the second bond within the double bond would involve an unhybridized p orbital on nitrogen and a p orbital on oxygen. In this last concept, I'm just defining the term stereoisomer, really. Stereoisomers are also called spatial isomers. These are compounds that have the same chemical formula, but they have different geoarrangement of atoms within the molecule. And this frequently comes about when you have double bonds present in the molecule. And the reason for that is that double bonds are fairly rigid and do not easily rotate. To help, I'm going to go ahead and draw this first example, and then I'll try to explain that concept. So this compound 1,2-dichloroethylene, there's 2 ways you can make it. So there's this way, and then here's the other way, where the fluorines are on the same side of the molecule. So this is called the cis configuration, and this is the trans configuration. Now, Each of the carbons is an sp2 hybridized structure, and then the second bond of the double bond is formed, and I'm going to again draw the picture here, where you've got a p orbital coming out of the plane of the board at you. And so I'll draw one lobe of the p orbital, and then here's the other lobe. Here's one lobe of the p orbital on this carbon atom, and then the other lobe. Okay, and so you have, when these two p orbitals are aligned like this, you have very good overlap, and that's a low energy configuration. But if you try to twist the molecule around, like bend it, can't quite see my hands, if you try to bend it like that, you're going to break that atomic overlap, and that's going to cause the energy to go up. And so carbon-carbon double bonds do not rotate very easily, effectively making these two separate molecules. Okay? One is in the trans form, the other is in the cis conformation. And trans and cis molecules will have different properties. For example, these two molecules will have different boiling points. That's what the term stereoisomer means. These are stereoisomers of this compound 1,2-dichloroethylene. Single bonds, on the other hand, they do rotate fairly easily. And so if we look at a different compound, 1,2-difluoroethane, that compound, I'm going to draw like this. We'll draw the fluorines like so. And then I'm going to draw the hydrogens like this, which indicates that the carbon has an sp3 hybridization. Okay, so notice that there's 1, 2, 3, 4 electron pairs around each carbon. So that's the tetrahedral or sp3 hybridization. Now, there's 4 equivalent sp3 hybrids, and then the bond between the two carbons is a sigma type bond. And no matter how you twist these two groups relative to one another, you're always going to have the same overlap between the two carbons and their sp3 hybrids. So there's very little energy required in order to rotate about this carbon-carbon single bond. And so as a consequence, these molecules are just spinning around. They're just rotating around. Okay? And so all sorts of different rotational configurations are going to be possible for this molecule. Now they're asking us to draw them. I'm going to go ahead and skip that. But in any case, that's the distinction between that's another distinction between double bonds and single bonds. You can easily rotate about single bonds. You cannot easily rotate about double bonds and triple bonds. They're essentially locked into place, forming what we call stereoisomers. Well, I'm going to go ahead and stop this video. And in the next one, we're going to discuss a completely different approach to molecular electronic structure theory, or molecular electronic structure, called molecular orbital theory.